Hello and how are you? Welcome to this tutorial yet another again of calculus. And I believe from the previous tutorial we also said in this topic it covers a wide ground. So we also split it up. We found that it has another name called elementary calculus, and we said it is divided into three parts. We have differentiation, integration, and also area approximation. So previously we looked at area approximation. This tutorial we shall begin now venturing into differentiation, and then finally when we are through differentiation we shall go to integration. I am your tutor Dick Joseph Adeli, but before we begin I would request us to humbly bow down for a word of prayer. Father Lord in heaven, you being the greatest mathematician, we come before you humbly asking that you be able to teach us differentiation as it is in calculus, and what is also required of us in this particular topic. Teach us with the stillness of your voice. Send us Holy Spirit to be able to explain everything in our ears, to be able to understand. Just let me pray. Amen. Quickly to our specific objectives of differentiation. By the end of this topic, you should be able to find average rates of change and instantaneous rates of change. Be able to find the gradient of a curve at a point using tangent. Be able to relate the delta notation of rates of change. Be able to find the gradient function of a function of the form y is equals to x power n, of which n in your case at this level n will be a positive integer, but when you get to higher levels you shall be able to find that n can also be a negative integer. You shall be able to define derivative of a function, derived function of a polynomial, and differentiation. You should be able to determine the derivative of a polynomial, find equations of tangents and normals to the curves. You should also be able to sketch a curve. You should be able to apply differentiation in calculating distance, velocity, and acceleration, and finally apply differentiation in finding maxima and minima of a function. So all these will be our objectives, so please be keeping in touch with them so that you're able to know where are we and where are we going. In this tutorial we shall be able to do mainly one thing: introduce differentiation and give the basis of differentiation, how it operates. Mainly I'm saying about the methods of differentiation. That's what we're going to look at, and then most of this shall fall into place. If you understand what you're going to do in this particular tutorial, the rest shall be a flowing river down the rocks that tend to give obstacles that cannot be able to hinder the flowing of the river. So let's begin our course in able to flowing out in this calculus journey. Now, you have learned how to be able to get gradients at different points, but in this case we should be able to learn, I believe you also from science point of view, chemistry, biology, physics, not all lines that you get gradient from are straight lines. All gradients are not from straight lines. Gradients can also be from curves. So question, how do we get gradient at curves? That's quite strange, because you will find that at different points the gradient will be changing. Why should they be changing, and yet we should be able to find the gradient? That's what differentiation shall be able to explain in this case. But first we shall begin with a review, so that we may build upon what you know to what you don't know. First, you know how to be able to calculate the gradient of a line. That's a straight line, a linear line, a linear equation. So if you have such a line here, if you are told to get its gradient, you know that basically you begin by picking out 2 points on the x and the y axis, so that you may have the change in y and the change in x, which is basically noted as what we have said, delta y here and delta x. So basically you're saying there's a change in x and there's a change in y. So notice those points: change in, there's a change, there's a small change. And also I believe it was also really stated that when you're calculating for that gradient, it must be of a very small change, or else if you pick a very large gradient, it will tend not to be very accurate. It must be very small. So that gradient, that small change in the points that you have must be very, very small. So this is what you have. And basically, if you pick 2 points, we shall have, for example, in the y-axis, y1 and y2, x-axis you have x1 and x2. Basically, your 2 points shall be x1, y1, and x2, y2. Basically, to get the gradient, you know that it will be, the gradient is denoted by m, so the change in y over change in x, which is simply delta y delta x, is equals to y2 minus y1 divided by x2 minus x1. That gives you the gradient of that line. Very straightforward. But, question, how do we get the gradient of a curve? Because a curve is not direct as we have seen here. Let's just look at an example of a curve so that we may be able now to see how the gradient is gotten. If I have my x-axis in that particular manner, I'll have my curve like that. So notice at different points, we shall have different gradients. If you can notice that at every point there shall be different gradients depending with the slope that is there. So basically here, now we're going to work with something known as a tangent. A tangent is basically a line that touches a curve at a specific point, only one point. So in the case of curves, we get gradients at specific points. So we're going to find from the equation of the curve, we shall now have to derive another equation that shall be able to give us the gradients at different points. The general equation that shall be able to equate to gradients at different points, such that we don't calculate for gradients at each and every point. It will be very tedious, don't you think? Imagine calculating for millions and millions of points on a line. It shall not be very easy. Basically, we shall be able to derive an equation from the general equation of that particular curve that shall equate to the gradients of that curve at specific points. That's what we term as instantaneous change. A curve is not with a general, it doesn't have a uniform gradient. It changes instantaneously with respect to the independent variable. It may be time, for example, with respect to distance. Notice when you drive a car, the car will not just have a uniform velocity from your home to town. It depends. For example, in a jam, you'll move at a very low velocity. When you are at a very high speed road that is fast moving, your speed shall be high. And if you represent that into gradients, into a graph, you shall find that the graph shall have different gradients depending with the velocity you are in. Or for example, you wanted to focus on acceleration, it shall also be different. So that is what differentiation is all about. The rate of change. That's what differentiation is all about. So basically, we shall, for example, take note of a point, then draw a tangent, and then from this particular tangent, we shall now be able to get the gradient at that specific point. That is basically what we can be able to deduce, but we shall learn how to be able to get the gradient function, which is simply called a derivative. Let's now get to work. The gradient at a point on the graph is equals to what we know as the slope of the tangent to the curve at that point. The process of finding the gradient at a point is called differentiation. That's something you need to note. For any polynomial, d over dx into brackets ax power n is equals to nax power n minus 1. Now this is a whole gymnastic that requires us to be able to explain, so don't be worried. What we basically have here is what we term as the rule of differentiation. We shall be able to explain this with the time, so don't be worried, just note it somewhere. By the end of this tutorial, you should be able to understand what this animal is. It looks very strange, but don't be worried, we shall be able to explain it. So with that, we shall be able to know that the gradient in this case, we know it's denoted by m, but in the case of calculus, it shall be noted as dy over dx. Differential of the differential of y with respect to the differential of x, or basically the derivative of the equation, shall be dy over dx. And in other cases, you'll note that you can also represent it by y prime. and there are very many more ways of denoting it. We shall be able to see that with time, so don't be worried. So in this case, we begin by dy over dx. It looks familiar with the one that you had, delta y over delta x, so it's not big deal, because the word delta is a Greek letter for d. So there are two ways of calculating the gradient of a curve, or basically differentiating. The first one is first order principle, which is the mother of all. The second one is what we term as the rule of differentiation, which basically is now a simplified version of the first order principle. So the moment you understand first order principle, the rule of differentiation shall fall into place. So please take note, as we'll be explaining these two ways, especially the first order principle, which is the mother of all, that shall help us unlock the rule of differentiation. Now in differentiation, this one thing you need to note, we heavily work with the independent variable. The independent variable most of the time is usually x. So this is what basically we usually work with. So for example, if you have an equation y is equals to x power this and that and that, x is the independent variable, y is the dependent variable. It cannot function, or it cannot be well defined without x, but x does not require y to be able to be defined. So that's what I was explaining here. In most cases, x is usually the independent variable, but always check. In some cases, an examiner may trick you, or in real life situation, someone may tell you, now we are working with velocities and displacement. In this case, we'll have our displacement as s, our time as t, and like so on. You'll not start crying and saying, no, I'm used to x. No. In that case, you have to know which is the independent variable and which is the dependent variable. Now let's start the differentiation process. We shall begin here with the first order principle. Now, if a curve is, for example, in that with that equation, we shall have that as an example. Y is equals to 2x power 2 plus 2x plus 1. Then any point on that graph is xy. Notice if you want to get the gradient, we basically pick 2 points on that particular graph. So that's what you're going to do. But we know that y is equals to 2x squared plus 2x plus 1. So the first point we shall have is xy. But we said we are working heavily with the independent variable, which is x. So we shall substitute for y and have our statement in terms of x. This is what I mean. So my first point is p, which is x, comma, and the rest is y. 2x squared plus 2x plus 1. Something you need to note. We heavily work with the independent variable. Now, the independent variable in most cases usually falls in the right-hand side of the equation, or basically the variable that does not require any other statement to be well defined. Notice x here being an unknown, it does not require y to be well defined. But notice if I erase this, what will be y equal to? It cannot be well defined. So that's what it means. So a collection of the independent variables help us define the dependent variable y. So my first point is p. Now the next, notice when we were explaining about, when we are reviewing getting gradients, we said there's a small change between the points, between y and x. But now because we are heavily working with independent variable, we shall pick a very small change in terms of x. So that's what we have here. To be able to get the gradient, we ought to have a second point, as we have known. So we shall take a very small change h along the x-axis from point P. That means point Q, which is our second point, shall be x plus h, and then each of the corresponding x's shall also have a small change in x. I believe it makes sense. If I'm taking a small change h in the x points, so each of the x coordinates shall get a small change of x. So far so good, I believe so. Now let us simplify our equation. I'll start working on everything. After that, we can now get the gradient between those 2 points. We know that the gradient of PQ shall be change in over change in x, and for me I shall decide to be able to begin by yq minus yp over xq minus xp. Now, if you don't mind, you may pause the video so that you may try working out on your own and see if you are going to arrive at the same answer, because it's good to try on your own. And if you fail somewhere, do not crucify yourself because you have failed. No, you are only taking lessons, and those obstacles make them to be opportunities, or basically what we term as stepping stones. So please pause. If you don't mind, you may pause the video, try working out the equation from what you know. We have the 2 points on the screen right now. Try working out with those 2 points, point P and point Q, with the statement that I've given you here, whereby I've said yq minus yp over xq minus xp. Now, I believe you have an answer somewhere. Let's go through so that you may refer also to your answer that you have. So notice m, which is the gradient as you have known, will be equal to point Q, which is twice into x plus h squared plus twice into x plus h plus 1, close the bracket, minus the second point, which is 2x squared plus 2x plus 1 divided by the first point, which is x plus h minus x. Open up every bracket. By simplifying everything, we shall have the following. I've simply written it step by step. I believe you can follow it up. So the first bracket where it was squared, believe from identities you can be able to note what I've done, which is x, which will be 2 into brackets x squared plus 2x plus 2xh plus x squared h squared plus 2x plus 2h plus 1, close the bracket, minus 2x squared minus 2x minus 1 divided by x plus h minus x. Now that's what we have. Simplifying this thing further, we shall have the following: 2x plus 4xh plus 2x squared, 2h squared, sorry, plus 2x plus 2h plus 1 minus 2x squared minus 2x minus 1 over h, x plus h minus x. Now, there are some like terms somewhere. Notice we have 2x and 2x squared minus 2x squared. We have 2x minus 2x. You have 1 and 1. So we can simplify everything. To simplify, I'll have this animal. In the numerator, it will be simplified into 4xh plus 2h squared plus 2h divided by h. Now h is common. We can divide all through. We'll have that. The gradient being equal to 4x plus 2h plus 2. Now notice, there's a problem. There's a problem. If we take a small change in h, as we said, should that small change again reflect in the gradient? I suppose no. Then what do you think should be the answer? Because now I'm remaining with the h. This h should disappear. Take note. This is not the gradient, since it still contains a very small change, h. We ought to simplify it to eliminate it. Now, we don't just come from the bush and cancel it out and say, now, this will be our equation. No, there's a step. One thing we ought to know is the knowledge about the very small change, h. The very small change, a very small change, a. I believe there's quite a number of repetitions there. The very small change, h. Now, a very small change, h, is hereby assumed to be 0. Why? Do we come from the bush? Let mathematics explain itself. Let's prove our assumption. Now, assuming we have this curve, pick a point where we want to get the gradient from. We have a point A, and I've reduced it from that so that you can be able to have extrapolated it from my graph, so that you can be able to find a reading. Now, because I didn't demarcate points here, this is just a sample. In yours, you have to have points. So this is my point A. I pick a small change h. This takes me to a point B. Now, if I draw a line between those 2 points, it does not give me a graph that is coinciding to point A. Notice, for me to get a gradient at point A, it must be in line to the flow of the graph. For example, if you are taking a graph of a line, assuming this was a straight line, the the gradient must be in line of that curve, of that graph. But here notice it's not in line. So we have to reduce this small change h further such that it coincides with the flow of the graph at that point A. Let's reduce it further. Not yet, but it has reduced. We reduce it further. Notice now it has now started behaving well. Reduce it further again. Almost behaving. We reduce it further again. So notice h is reducing smaller into smaller and smaller values. If I reduce it further, it will reach a point. We'll find a tangent at point A, of which point A and point B will be coinciding, and h shall be tending to 0. That's something you need to be able to always remember. H was our small change, but it reduced until it came to 0. So that's what we simply mean here. After getting our graph, our derivative, this h is a small change which tends to 0. Therefore, because h is equals to 0, our gradient shall be m is equals to 4x plus 2. Haha, does it make sense? H is a very small change. It tends to 0. So the moment x is 0, anything 0 multiplied by any number, 0. So you have 4x plus 2. But we said in ways of being able to denote the gradients in calculus, we use the following format. Y prime is equals to dy over dx is equals to 4x plus 2. Now you need to be very aware of this format. Either you can use y prime or dy over dx. This is now the language you shall be using. And even more shall come with time. So start being acquainted with such small stuff. Now let's go to the rule of differentiation. Now as we plunge our feet into this new differential site, we need to take note of these two equations we now have. Notice we first had our equation as y. The equation was y, find the derivative of y is equals to 2x squared plus 2x plus 1. But our solution finally came to dy over dx is equals to 4x plus 2. Question: what do you notice between those two equations? Please take a keen look. Atakama, even though it will take you quite a long time of span, please try to crack out what does this question really mean. Sorry for also interchanging languages there. What do you really think? What is the relationship between these two, or what can be found from these two equations? I believe you have a solution somewhere. If not, please pause the video and try cracking out on your own so that you may appreciate what I shall give you further. Now, these are the two that we have. If y is equals to a power x, axn, then there's something that should happen. Now, before we go to that, notice this derivative. Okay, something you need to note. Derivatives basically, after you have applied the you have differentiated function, or basically an equation. Okay, each equation in calculus is called a function. That's something you need to know. If you differentiate it, the result is what we term as a derivative. And this is basically what we call first order derivative. With time we shall be able to get to what we term as second order derivative. But don't be worried, those are terms we shall be able to explain. Notice there was a multiplication here. For the first term 4x, we got 4x by multiplying the coefficient of x squared by 2 and this power reducing by 1. Because if I don't write here the power, it simply means the power is 1. And then this next, it was the same gymnastics. The power is 1 multiplied by the coefficient, and then that power reduces by 1, comes to x power 0, which is basically 1 from indices. What happened to this 1? The 1 here has x to power 0. So if I multiply it by the coefficient, you find that this becomes 0. We shall be able to get an example so that this makes sense. But what I was simply trying to labor is, I believe you see that to get 4x, the coefficient multiplied by the original power, then that power reduces by 1, comes to 4x. Then the same thing applies to all the other terms. So if y is equals to ax power n, then the derivative will be this, what I was explaining. The original power multiplied by the coefficient of x, and then the power of x reduces by 1. NB. This rule is done for all terms in any given equation. So for example, if you add this, each of these terms must follow that rule. For example, this first term was 4x, the second one was 2, the third one was 1. Let's get an example just to explain what we have. So get the derivative of this equation by using the rule of differentiation. Before I give you my solution, please pause the video and try gambling about with what I've just tried to explain. If I take you back to the statement so that you're able to get it, that is the statement. Try fumbling about with the question I've given you if I give you my solution. Now I believe you have an answer. Let's confirm with what I have. First step, notice we have a 1 here. What we need to do is that all constants must be written in such a way that they bear the unknown function. Now, because you are a beginner in this particular topic, that's the first step I shall introduce you with. But with the time, we shall always learn how to play with the constants. So the first step, you rewrite everything in terms of bearing the unknown. So notice 1 can be written in this format. From indices, you know that x power anything to power 0 is 1. That's why we didn't bother ourselves by writing that power x there. So this equation is simply what we have here. Then the rule of differentiation, we said it applies for all terms in any given equation. So basically, if you apply the rule of differentiation here, this is what we shall end up having. The first term, for example, shall be 2 multiplied by 2, the power multiplied by the coefficient, and then the power reduces by 1. The second term, which is 2x, the power is 1 multiplied by the coefficient, and then the power reduces by 1. And then the next, which we said is power 0, multiplied by the coefficient, then the power reduces by 1. The solution here shall be 4x power 1 plus 2x power 0, and anything multiplied by 0 is 0. So simplifying that, we shall get to 4x plus 2. Make sense? I believe it, so it makes sense. Now let's get some important notes that are quite good to be able to take home before we call it a session. The gradient function of a function y is equals to x power n is dy over dx is equals to x prime is equals to nax power n minus 1, where a is the coefficient of x, which is called rule of differentiation. This rule must always be with you. But what I'm laboring is understand the first order principle. If not, please reduce the tutorial so that we're able to understand. If not, please try getting in touch with me so that I'm able to explain it much further. In differentiation, we differentiate using the differential rule whereby it's term by term. That means every term is multiplied by that particular rule. When differentiating a function, this is very important now, it is important to work with a simplified expression. For example, you may be given a situation like this. Y is equals to, in the numerator you have 4x power 4 minus 16x squared over 2x. We simplify this first before we start differentiating. We simplify it out, notice that we can derive the same equation as 2 cubed minus 8x, and that simplifies our problem very far. And I believe that comes to our derivative. Now that's the answer. Please try fumbling about using first order principle first. See if we shall get to this. Use the rule of differentiation. If you can get to this, that's how you shall be able to work. In this particular case, I'll not leave you with very lot of work. I just want you to fumble about with the examples I've given you. And then the next tutorials to come, we shall be able now to dwell now with examples and how to play around with various equations. Now, something you need to take home. There are different ways of denoting equations and derivatives in calculus. That means there is no single no single uniform notation for differentiation as proposed by different mathematicians. So different mathematicians, for example, Leibniz, we have Newton, they had different ways of denoting their findings of calculus. They were all the same, they all result the same answer, but with different notations. You'll find others saying like the following. We know that our equation is written as y is equals to x power n. But notice I can write this in this way. Y is equals to f of x is equals to x power n. F of x simply means the function of x. Notice y is written in form of x. It's a function of x. What does it mean? X is the independent variable, and it's one used to define x. Define y, sorry. So y is a function of x. So it can be written in this particular form. That's what it simply means. And in other cases, you may find that instead of somebody writing f of x, he writes g of x, he writes h of x, he writes what? Funny names. We shall explain that. Don't be worried. And our derivative, we said this is what we have. But I can also rewrite it in this particular form. Y prime is equals to dy over dx is equals to f prime x is equals to n of a x, power n minus 1. All this is still calculus. The two are equal. So we shall explain this. So this shall be covered in the next tutorial, where we shall now personally dwell on this particular subject. Why do we have very many notations of different equations and derivatives in calculus? Otherwise, success in your preparations. May God bless you abundantly. Meet you in the next tutorial.